Hello and welcome to MAE 113 Calculus for the Liberal Arts. My name is Richard Kohar and this is Lecture 15. Lecture 15 is on position, velocity, and acceleration. And what we're going to do today is collect some data. I've set up a tape measure, and what we're going to do is we're going to drop this ball using this specialized camera equipment. And we have a strobe. What we're going to do is we're going to pulse this at, we're going to do 18 flashes at 25 hertz, or that's going to be 25 flashes in a second. And so what we're going to do is we'll drop that ball and record that. The idea behind a strobe and why we strobe it is, instead of using continuous lights and using video, we won't be able to get a crisp image of the ball. So, and unfortunately, the camera itself has a slow frame rate. It's only got 5 frames per second. So what we're going to do is we're going to leave the shutter open. We're going to turn the lights off. So we'll leave the shutter open for a second. And what this is going to do is it has short bursts of light, and it's going to freeze the ball as it falls. So let's go over to the, what we can see is we've got this tethered to the computer, and we're going to turn off the light and drop the ball, and hopefully we get some data. So let's turn off the light, and hopefully I can hold this, and what I'm going to do is I can trigger it with the tether software, and 3, 2, 1. Oh, of course the flash didn't trigger. And now I have to find the ball. Where did I? It dropped over here, so gotta go pick this up. Oops. And this is the mouse that I'm using to trigger. We'll turn off the light again. Oops. And this is the fun of doing this by yourself. So, oops, and I didn't drop it because I had the mouse in my hand. And yep, you can see that on the monitor there. That's not what we wanted. So let's try that again. Just a second, come on. Okay. And okay, and I'm going to drop it now in 3, 2, 1. Perfect. So now we can go over to the computer and we can actually have a look. Yes, we've done it. So we've been able to get at least some of it. And so we got that a couple times. You can see there's my phone that I'm using to record on, and there's the ball. And what's kind of nice is, kind of just to illustrate this, that objects kind of, when we're dropping it, it falls down usually in a straight line. But the nice thing, let me just find where the ball went again, and it dropped over here. So, what I'm going to do is I'm going to put the camera down for a second, and I'm going to throw the ball up. So, and so you can have a look that it has a parabolic shape. Hello and welcome to... Okay, so we had done some... So hopefully you enjoyed that. What we were doing was we were collecting some data, and that was just a little bit filmed previously, and the reason for that is because I just don't have the equipment to live stream it on the spot. So what we can do now is we can have a look on our screen here, and so probably we can, and the nice thing about that is we can actually increase and zoom in on it, and we can actually have a recording or a measurement of each, can see where the ball was at each time step. And just to give you also just a little bit nicer view of that, that was the parabolic Now, I wasn't trying to throw it in a parabolic arc, but basically you throw the ball up, it'll hit a point where the velocity is 0, and then it comes back down. So again, it's a model for movement of a ball. It's parabolic. It's not always the case. There's some other issues that could happen, but again, it's good enough for our mathematical model. So what we're going to do is we're going to come up with a model for it. So we can read off some of this data. I'm going to try to do it as best as I can. I'm used to just what I would usually do if I was doing something like this. I would go and print it out, and then I would use a ruler. So what I'm going to do is I'm going to put the time. So in this section, I'm going to have time. And what I'm going to do is I'm going to write the measurement over here. So this would be like our x. And the thing is that this is going to be in inches. The next thing that we have is I have to convert this. I'm going to convert this to in centimeters. And then finally, I'll do this in meters. So again, roughly what we can do is zoom in. And just kind of reading off of that, I see that's about, say, 68 and around 1/4 of an inch. And then we kind of just work our way down. Here's around, I don't know, about this point here. So let's say about 65. 65, and let's say 13/16 of an inch. Oh, of course, it's not going to like that. 13/16. Okay, well, if it doesn't like that, I can always... It's 0.8125. And again, we just keep working our way down, collecting our data. Let's say that's about 62.8125, or that was a 1/13th of an inch. Now you might be asking, like, you can see the outline quite clearly. Unfortunately, the contrast isn't great. The way that I would have done this usually is on a black background. So if you wanted to do it correctly, you would use a black background, and I only had a what's called a Savage Fashion gray background, and you'd use black, and then I would use a higher power to get the so you could see the ball a little bit more with more contrast. So that's about 50 1/4. So is there any questions about what I'm doing? Or I think it's fairly straightforward. That's about 44 7/8, so that's about 875. And so hopefully what I've done well enough is that I should have a parabola when I'm doing it with respect to time. So that's that looks about 32 3/4 of an inch. 3/4 of an inch. And that's about 26. And we're getting a little dark. Let's see. Let's say that's about 1/18 5/8. So just going over here, 625. And do we get one last data point? Ooh, that's pretty dark. I don't think It's coming through very well on the camera, but it's about 11. Okay, so I can close that. I will increase the size on this. Okay, so, oh yeah, I should also mention that we're using LibreOffice, the calc or the spreadsheet software. Roughly, we knew that it was 25. So you know that it's 25 hertz, and 25 hertz is means that it's 25 times per second. So it should be 0.04. So we start out at 0, and then 0.04, and then 0.08, and so on and so forth. Oh, of course, it's not going to undo. I think what I'm going to do, though, is I'm going to take this one and multiply it by 2. I'll take A3 and multiply it by 3. Let's just call this 0, 1, 2, 3. So in total, we got about 11 data points. Let's see if we can do it that way so it's a little bit faster. There we go. Okay, so I was using a tape measure. It was in it was in imperial. So in inches, we're going to convert that to 2.54. There's 2.54 centimeters in every inch. So it was about 173 centimeters. And then to convert that to meters, divide that by 100, because there's 100 centimeters in a meter. And done. Okay. Now, to do the data plot, I'll select this and insert. We're going to insert a chart. We're going to plot this. We don't need a bar graph. We need a scatter plot. Next. Now, of course, you're probably thinking like, oh, this is, why do we know it's going to look like a parabolic arch. I already showed you. So what this is this is a calculus demo, and along the x-axis this is time in seconds, this is height in meters, and I don't think we need to know the column C. So I made a little chart here, and you can see it's kind of got that nice arch to it. Okay. Now, what we need to do is we can fit a curve to it. So we have these individual points. I wasn't able to sample at every point there. So what we can do is put a smooth, continuous curve on that. And I can do that by inserting a trend line. That is a terrible line of best fit. A linear function does not describe this very well. In fact, we need a degree 2. And so degree 2 is, we know, is quadratic. So I can apply that. The other thing I want to do is I'm going to show the equation, and I'll also show the coefficient of determination, the r² value. And we'll go OK. And there we go. We actually have, well, looking at the r² value, which is kind of an indicator or measurement of fit to the data, it's doing pretty good. There's about 3 or 4 decimal, 4 decimal places of 999. There's our second degree. So the thing that we can look at initially, there's our Y-intercept, which is right here at 0, and it's 1.7378. So that's roughly 1.73 is where I dropped it from. So that's kind of our starting point, and that was kind of where we end. So
There are a little bit of an issue when I saw kind of this. The data was, I think, is fine, but I think that the timing actually from the strobe is a little off. So what we can actually do is, in real time, which is kind of nice, we should be able to, maybe I'll insert a column before, and I'll put the times here. Oh, maybe I won't. This time is a little bit off. So I think it's about 3.75 seconds. And so what I'm going to do is move this down. No. Okay. So it'll become clear why. So we actually now have a function that we can analyze. So let's switch over to my paper. And what we have, I'm just going to write it down to maybe 1 or 2 decimal places. So we got 4.786 x squared. And this is minus 1.57. We're going to use 3 decimal places, then it's going to be to the 4x plus 1.738. So this was what we had. So this is for the ball drop. And so there is our position function. We also know that, so that was what we came up with. We can write it a little bit nicer. So what we're going to do is, we're used to writing it with position as x, and then we're going to write it with respect to time. So again, I'm just going to rewrite it to like this, just changing my variables. 6t squared minus okay. So we also remember that our velocity is the change in position. Or it's also the derivative. So we can actually find what the derivative of that is. So the velocity, which we can also write it as v, so if I start to take the derivative of this, and I am not going to lie, I am going to pull out my calculator. So we're going to do the calculator, and I know that it's going to be 4.786 times 2. So the 2 comes down in front, and it's going to multiply it by that. So maybe I'll write that step out. if there is something on a test, for instance, that you can't do with a calculator very simply, you could leave it like that. That'll be okay. And then the degree drops down by 1, so it becomes from 2 to 1 minus 1.574. So I'm going to take that. So I have 4.786. I get 9.572 t minus 1.574. So there is the velocity, and also from that we should be able to do the second derivative of the position function, which is the acceleration. So the acceleration is the first derivative of the velocity, or it's also the second derivative of the position function. And this is straightforward enough that if I take the derivative of this, of the velocity, then I'm just left with, oh, and I also have to remember there's my negative sign, negative 0.572. Of course, this is our position, so this is in meters. Our time is in seconds. And then our rate of change then becomes, this is in meters per second. And when we get down to the second derivative, this becomes meter per second squared. Let me just have a look at the chat. Are there any questions so far what I'm doing? Excellent. Okay. Now, some people might look at that and there is a little bit of an experimental error. That's why I'm thinking maybe it's the timing that's a little off in terms of this. I know, for instance, that from physics, that the gravity or acceleration due to the Earth's gravity is approximately 9.81 meters per second squared. It kind of varies a little bit across the Earth because we've just of the shape of it. So around Kingston, we're around 9.80, but 9.81 is kind of the standard number that they give to everyone. So there's a little bit of experimental error here. So notice that it requires that I'm taking that number, I'm multiplying it by 2, which means that, again, if we were going back to kind of our data, and I said, oh, I thought it was maybe like 3.0375, maybe I want to try 8 and kind of apply it like this. Am I getting a little bit closer? Then, oops. You pull out the calculator, and I want to look at what the acceleration is. I'm just wanting to take this number here and multiply it by 2. 4.66 times 2. Nope, I even made it worse. So you'd have to play. I think though it is a little bit in the timing of the strobe, and probably also due to the inaccuracy of my reading of the image. So hopefully that kind of illustrates a little bit of the dynamics that we see. It's fun. That's kind of the physics of it, and I wish I was able to do stuff like that in class and show you that, but hashtag COVID. So what we're going to do now is we can do a couple more exercises in this. So we were talking about position, velocity, and acceleration. What's also kind of the nice part about that is when we do actually have a function like that, like this, I am able to now calculate what the height is at any point during this time interval. So, you know, if I want to actually find out what it was at 1 second, so let's just jump back to the paper. If I did want to find out what it was at 1 second, well, then I just substitute the values in for 1. So it's minus 4.786, 1 minus 1.574, that's times 1, plus 1. Okay. So again, that's kind of the nice thing about that. Let's do an example now. Hopefully that was somebody reminding me. Okay. So here's an example. So let's say that I had a cliff and I had some stone at the top of it, and then I was going to drop it off. So I'm going to drop it from a height of, let's say, 122.5 meters. And the velocity is roughly 4.9. So we get kind of a, let's see, what is the position function? So I know that it'll follow some sort of function. So it should be, let's say, x of t. And we start at 122 meters, 0.5 minus, and it's going to fall 4.9 t squared. So that's going to be the position function, you know, until it hits the ground. So kind of, you know, there's standard questions that could be asked, which is, you know, find the velocity after 1 second and 2 seconds. So to find the velocity, it's the derivative of the position function. So that is a constant. So we, you know, it's 0. The derivative of a constant is 0, so it's 0. And then I'm left with this term right here, which is a minus 4.9 times 2t. So we're doubling that. So again, 9.8, which, that's good. That's measuring, that's what I expect roughly for the gravitational gravity of the Earth. So it's minus 9.8 t. And what else? What else can we do? So that's the velocity. Oh, yes. And we're supposed to now find what the velocity was at 1 and 2 seconds. So substituting in our values of, here's 1. So it's minus 9.8 times 1, 9.8 meters per second. And the velocity at 2 is 9.8 times 2. So 98 is 196. So 19.6 meters per second. Here's an interesting question. When, so that basically means t equals at what? When will the stone hit the ground? So that means that we have to solve some equation. When it hits the ground, so that would be when the position is 0. So that means that it's our position, which I was thinking height. That's why I wrote h. But our position is x. And so that's that original function minus 4.9 t squared equals 0. And now what we need to do is solve for t. So I get a minus 125.5, sorry, 122.5 and minus 4.9 t squared. I have t squared over minus 122.5 over minus 4.9. Those, I have a minus and a minus, that becomes positive. So I'm left with 122.5 over 4.9. Now, I'll pull this out because that might not look so great. It's 122.5, enter it, 4.9, and I want to divide that into it. I get that is equal to 25. So t squared is equal to 25. So t is equal to square root of 25, which we can do without the calculator, and that is 5. So therefore, the stone hits the ground at t equals 5 seconds. So you just drop it. And again, we're not introducing any, we're not like throwing it down into the ground. Like we're not doing that, like really checking it. We're just kind of just dropping it. And so it's just accelerating due to gravity. So again, 122 meters. Yeah, 5 seconds. That's a long time. Oh, well then the other question is you know, what is the velocity? Of the stone when it hits the ground? Well, we already figured out that it hits it at 5 seconds, so that just means that we're substituting that value of 5 into the velocity function. And the velocity function is up here, which was the 9 minus 9.8 times 5. So 8 times 5 is 40. 9 times 5 is 54. 54 plus 4. No. 9 times 5 is 45. 45 plus 4 is 49. And we all need more coffee in the morning. 49. And that is meters per second. So that's our velocity. So that's how fast it hit the ground. Now, the next question that we could ask D, which is, what is the acceleration of the stone and going back to our V, we know that when we take the acceleration, it's the derivative of the velocity function. And what's nice about this is we just need to take the derivative of minus 9.8 t. And so it's just left with 9.8. And in this case, it's meters per second squared. There we go. Let's do maybe say another example. So let's say that the position function of a particle, it follows a position function. We'll say t cubed plus 2t squared plus 2t. And that the x is in meters and t is in seconds. So this is a particle moving. And so we can quickly find the velocity and the acceleration. So the velocity, again, taking the derivative of the position function. So I have 3t squared plus 4t plus 2. And the acceleration is equal to the derivative of the velocity And so taking the derivative of that is 6t plus 4. So, you know, a question would be like, what is the acceleration at, say, t equals 3 seconds? So again, just substituting in that value of 3 in there. And again, I am careful because the velocity is in meters per second, and this is in meters per second squared. So asking again that time of t of 3 seconds is okay. I can substitute that in. That's kind of what the original function was based in. You know, they were sneaky last time when we had a question where we had it in seconds, but then they asked us, oh, what was it in an hour? And that was not, you know, seconds. It was, we had to convert that hour into 3,600 seconds. So I have 6 times 3 plus 4, so 18 plus 4 gives me 22 meters per second squared. Can we go to jerk? Yes, yes, of course. And yes, we can do the jerk. Just to make sure that, like, if you don't have a term like where the acceleration is 9.8, remember the 9.8 is usually if we're dropping something, like it's acting under gravity. But in this case, a particle moving, well, this could be something like a car or some sort of, this is a cubic, so it's going to have some sort of acceleration. So it's something like this, it's moving on a line, or, you know, it's you know, it's not acting under gravity. So, but yeah, let's do the jerk. So, and of course, the jerk is the, don't know what letter I'll pick. Let's, if everyone's okay with J, I'll pick J. And that is equal to the derivative of the acceleration. And what's nice about that, it's just 6. I've been waiting to use that mathematical term for the whole lecture. Okay, perfect. It's good that somebody was waiting for it. I like a good punchline for a lecture. Every lecture should have a good punchline. Okay. What else? Oh yeah, what was I going to talk about? Notice that, oh, don't be the derivative of the acceleration. Yes, exactly. So what we were doing was we were looking at rates of change. So we had a rate of change in position, we had a rate of change in velocity, we had a rate of change of acceleration. So I mean, like, and jerk. But again, notice that if we didn't have some information here, going backwards doesn't work. So for instance, if you just told me that, let's do going from the acceleration to the velocity requires me to integrate. So I have the, oh yes, I want to go from the velocity to the acceleration. That is something I need to integrate. So what I have here is 6t plus 4 dt. And then using our power rule for integration. Well, okay, I can write this out explicitly. So I have 6t dt plus the integral of 4 dt. And again, that's a constant, so I can pull that out in front. Oh, and same thing here. I could pull that 6 out in front. So I'm left with 6 times, and then what I have is t. And remember, when I'm taking the integral of x to the n dx, it's 1 over n plus 1, x to the n plus 1, plus a constant, and does not apply when n cannot equal minus 1. So that's multiplying that. So this degree goes up from 1 to 2, and I need to multiply that by a half, plus I have 4. This is interesting. So you can think of that as x to the 0. So then we're going from 0 to the 1. So we're going, so in this case right here, I'm really doing kind of x, or maybe I should use like that. So the 0 goes up to a 1, and then we divide also by the 1 as well. So I'm still left with x to the 1 plus c. So in this case, I'm using dt, so that's to the t plus a constant. And then I have 6 divided by 2 is 3t squared plus 4t plus a constant. So again, I'm getting back to this equation up here. I have 3t squared plus 4t plus 2. But see, I'm missing part of that information because when I differentiate, I lose that constant. So again, you would have to tell me some sort of information to get back to that too. So for instance, you know, I don't know. See, like, you'd have to tell me some additional information. For instance, you'd have to tell me that the velocity at times 0 is equal to 2. So that when I start to do that, now I can substitute that. I have 3t squared plus 4t plus c equals, and we're told it's 2. And we also know that this is at 0. So 3 times 0 squared plus 4 times 0 plus c equals 2. These are 0, this is 0, so I'm left with c equals 2. And then I could conclude that the velocity is 3t squared plus 4t plus 2. Okay, so just to wrap up, we did precision, our velocity and acceleration, as well as some jerk. And the assignment is posted online, so make sure you check it out. Also, we have our test, not next week because that's reading week, but it's the following Thursday. So 2 weeks from now, it's on the 23rd. Just a second, let me double check. On the 25th. We have the 25th is when we have our test. It's during our regular scheduled lecture hour. We'll have some more details coming out what we're probably going to do is have it invigilated through Zoom. So you'll have to print off something and then sit in front of a camera, and we basically watch you write out your solutions. And then you scan it using a phone or a scanner, and you submit it through the Moodle page. But more details about that and how that's going to go is going to follow. If there are any questions, again, I'm just an email away. We have office hours starting in about 10 minutes. So if there aren't any other questions for the lecture, I wish you all a enjoyable reading week, and we will see you. Can I see you for office? Of course, everyone is welcome to office hours. We're starting it in 10 minutes from 1 p.m. to 3 p.m. Eastern Standard Time. Okay, excellent. I'll see you all soon, and enjoy the reading week. Take care.